Arduino audio spectrum analyzer with an OLED display. I've always wanted to do this. I first saw this project implemented over at Learn Electronics, who saw it implemented by CBM 80 Amiga. So now I'm doing my version of it, which is not really much different, but I've added a bunch of comments for my own purpose. This uses the fixed point math FFT library over at that link, and this has changed hands a lot. So on this page there's a link to the GitHub repository. This is not the originator of the code, but these download zip files here, I was able to use this to install a library in Arduino, so I didn't have to go and create folders and mess around. So I actually used this zip file, but over in GitHub, if we go down and look at the source, which I am very afraid of, we're not going to analyze this at all, but this goes as far back as 1989, and then 1994, 2006. Then it started getting mentioned in Arduino forums around 2010, and there's several threads that develop around this, so this is the latest copy that I'm aware of, and this is what I was using. I don't know much of anything about digital signal processing and fast Fourier transforms or discrete Fourier transforms. I just generally know that you take some time domain data, like an audio sample, and you run it through an algorithm like this to do a Fourier transform, and it involves multiplying the real time data by sine and cosine waves, and I'm gonna stay up at the high level where it's nice and safe and I just call the library when I need it. So I'm using my OLED SSD 1306 based display. What I do know about FFT is you give it a single real number, and after it's transformed you get back a complex number which contains a real and an imaginary component. So we store the real and the imaginary components in two separate arrays, and we're taking 128 samples overall. So we read in 128 samples of analog audio, then we throw it down to the FFT algorithm, and we get back 128 real and imaginary numbers, giving us a complex vector. So for a given frequency that comes back from the FFT algorithm, where you have a real and an imaginary number, on a graph, the real number goes along the x-axis, and then the imaginary number goes along the y-axis, and that final point at the real and imaginary coordinates gives you a vector whose magnitude is that frequency strength that we're looking for. That tells us how much of that frequency component is present in the audio that we are sampling. So this is basically a right-angled triangle. Hypotenuse squared equals real squared plus imaginary squared. So to get the length of this hypotenuse, or the magnitude, you take the square root of the real side squared plus the imaginary side squared. So now that we're back from that tangent, we get our real and imaginary FFT results in these real and imaginary arrays, and our OLED display is 128 wide and 64 pixels high. So we're leaving a little bit of a margin. We're only going to go 60 pixels high with our Y direction on the OLED when we are drawing the bar graph. In the main loop, after we do this setup, this is where we basically read in 128 samples of audio on the analog port. We throw those 128 time domain audio samples into the real array. Since we don't have any imaginary data on our time domain original signal, we just give it 0. In the FFT algorithm, these real and imaginary data points are characters which are signed numbers between -128 and 127. But when we read in on the analog port, we're getting a number between 0 and 1023, so we need to scale it down to fit within -128 to 127. So we divide by 4 when we take a reading, and then we subtract 128. So if our reading is actually 0, the lowest we can get, we end up with -128. And if the reading is 1023, the highest we can get, we end up with the highest of 127, so it fits scaled within that character variable. Once we have read in 128 samples into our array, we throw it down into the FFT algorithm, and it will write back the real and the imaginary result in the same array. So now we have that vector data where we could draw on a graph real and imaginary coordinates and calculate the magnitude of that vector. And that's what we do. So we clear the display. We're going to overwrite it with whatever the current data is. We start by going to the top left corner of the display and we just write a little message. Then we need to go and calculate the magnitude of each of those converted frequencies from the FFT algorithm. So the magnitude of the frequency for each of those vectors is the square root of the real data squared plus the imaginary data squared. And that's the value we need to draw on the display as a graph. So what frequency range are we displaying on our bar graphs? Well, using the Nyquist theorem, whatever the maximum frequency of the signal is that you're trying to sample, you've got to be sampling at least twice as fast, if not more. With the Arduino running at 16 megahertz, it ends up being about 9 kilohertz that we're sampling with. So that's got to do with the fact that we are using the analogRead function here, and that's got some overhead on it, but basically the default settings for the analog conversion includes having a prescaler of 128, so you've got a 16 megahertz clock divided by 128, and that gives you 125 kilohertz to work with. But the analog conversion takes 13 clock cycles, so 125 kilohertz divided by that 13 leaves you with about 9.6 kilohertz. And because we are going through a loop and we're doing some other operations here, in the real world, by the time we're done with our overhead, based on observing the operation of this circuit, we're about 9 kilohertz sample rate. So that means the maximum frequency that I can sample is 4.5 kilohertz, half of that, or else I'm violating Nyquist requirements. So if I'm sampling at 9 kilohertz and I'm taking 128 samples, each of my frequency bins are going to be 70 hertz or so wide. This stuff kind of confused me a bit, so suffice it to say we are sampling at 9 kilohertz. You divide the sample frequency by how many samples you're taking, and that's how wide each frequency bin is going to be. And a frequency bin is basically a bar on your bar graph. So if I'm taking 128 total samples at a rate of 9 kilohertz, but I can only consider data up to 4.5 kilohertz to be valid, we basically ignore the upper samples and we only use the bottom 64. We still have the upper 64 values, but they're going to contain unreliable, invalid data because it violated Nyquist. If we try to put in a 5 kilohertz signal, we need to sample at least 10 kilohertz to get an accurate representation here. So you got 64 samples you're working with, and each of those bars on your graph are going to be 70 hertz wide, and so 64 times 70 hertz wide equals about 4.5 kilohertz. That's how it gets all split up on the bar graph. This stuff was throwing me for a loop. I wanted to actually explain it a lot better and go a lot deeper, but I just ended up confused. So I just tried to write comments as good as I could to explain some of this stuff, and you can do your own research and maybe explain it back to me and we can all figure it out. I'm not really here as an expert, I'm here as a learner. So since we only care about the bottom 64 samples out of our total 128 samples, because that's where our valid sampled frequency lies, we run this loop for those 64 samples. We calculate the magnitude of each of those real and imaginary components, and we draw a bar on the bar graph representing the frequency presence of each of those 70 hertz wide bands. And that's basically the project. So regarding the aliasing, one thing that I noticed when I was playing around with the signal generator, I saw this folding issue. So long story short, again, because I don't fully understand this, but this is our sampling frequency, so in my case it's 9 kilohertz. So the Nyquist frequency that contains valid sampled data is half of that, or 4.5 kilohertz. What this essentially says is, as you try to sample frequencies higher than half of your sampling rate, the Nyquist rate, you're going to start seeing aliases reflected on the other side of that Nyquist rate, as well as at multiples. But to put it just intuitively, visually here, let's say I'm at 4.5 kilohertz. It's at the margin of what I'm allowed to sample. If I go to 4.6 kilohertz input signal, I'm going to see a ghost down here equally away from my Nyquist rate of half 9 kilohertz or 4.5. So I put in 4.6, I'm going to probably see something around 4.4 kilohertz. If I put in something at 4.7 kilohertz, I'm going to see it echo down about 4.3 kilohertz, and so on. And I saw this with the signal generator. I was scanning up and everything was fine, and then I kept increasing and I was seeing the spectrum go backwards. And then I found out about this. Here's the Arduino Uno with the OLED display running the spectrum analyzer code. I have a scope here and I'm using a signal generator for now with a sine wave at 4 volts peak to peak to get a reasonable range of the 5 volt analog input on the Arduino. And I'm starting at 10 Hertz. I want to try sweeping the frequency up and see what happens on the spectrum analyzer. So starting at 10 Hertz, I have barely any activity. Maybe that's just noise down on the bottom end on the left. So I'm going to increase by 10 Hertz at a time for now. So already at 20 Hertz, it's starting to show some activity. 30, 40, 50 Hertz. So we are detecting a strong signal at about 50 Hertz. 60, 70, 80, 90, 100. And now our energy is kind of being divided between two side-by-side areas. So now I'm going to start going up by 100 Hertz per step, and I will change the scope's horizontal so we can show 200 Hertz, 300, 400, 500, and we are sweeping up now in the frequency band on the spectrum analyzer display. 600 Hertz, 700, 800, 900, 1 kilohertz. So we've gone about a quarter of the way up the display at 1 kilohertz. We should expect to get maybe 4 kilohertz for something. So we'll keep going from 1000 Hertz, 1100, 1200, 13, 14, 1500 Hertz, 16, 17, 18, 19, 2 kilohertz. Stretch this back out. So we're about halfway up our frequency spectrum and we're at 2 kilohertz. 2.1 kilohertz, 2.2, 2.3, 4, 5, 6, 7, 8, 9, 3 kilohertz, and we are about 3/4 of the way across. 3.1, 3.2, 3, 4, 3.5 kilohertz, 3.6, 7, 8, 3.9, 4 kilohertz. We're getting close to the end. 4.1 kilohertz, 4.2, and now let's watch what happens as we get closer. 4.3 kilohertz, 4.4 kilohertz, and we have a big peak there, and 4.5 kilohertz. It's kind of hard to tell, is it actually still picking up the proper frequency because it's right on the edge. So this again is 4.4 kilohertz. 4.5 kilohertz may or may not be a true reading, but when we go to 4.6 kilohertz, we actually started going backwards because we have a really tiny peak at the far right and then this huge peak one away. So let me go back again to 4.5 kilohertz. We've gone up. 4.6 kilohertz, we've gone backwards. And if I keep going up in frequency, 4.7 kilohertz, 8, 9, 5 kilohertz. So we're going up in frequency, but now we're kind of stepping backwards. So just for fun, let me set a sweep on here and do a sort of a Knight Rider thing. So I set it to have a 5-second sweep up and then back down, going from 50 Hz to 4.4 kHz. Of course, the scope is having trouble locking on and keeping up with this, but the spectrum analyzer is showing my frequency is going up and back down. What better audio track to test a spectrum analyzer than something called 555 by Endless Love. It is in the YouTube copyright-free, attribution not required library. You're free to use this song in any of your videos. All right, let's do that. So I'm going to hook up this Max 4466 amplified electret microphone module and play the music over a speaker and capture it, bring it to the analog input, and see what happens. Well, that wouldn't be my first choice in music, but it works. So, all in all, I learned a couple of things on this project, and maybe I can turn it into something bigger later.